The second question of our Objective 4, dealing with phase changes. What is the enthalpy change during the process in which 75 grams of water at 20 degrees Celsius is cooled to ice at negative 70 degrees Celsius? The rest of the question are giving us the constants we need for those line segments. Again, let's begin by drawing our XY axes so we begin to visualize how many line segments there are involved with this particular question. When I draw my XY axes, I label on the Y that we have temperature measured in degrees Celsius. On the X-axis, I have heat measured in joules. The first temperature, as I read my problem, was 20 degrees Celsius. The final temperature is below that. It's at negative 70 degrees Celsius. Negative 70 degrees Celsius. Between those two, 20 and negative 70, I will have one phase change occurring at 0 degrees. To think about the journey of this problem, we will start with point A at positive 20 and cool it until it reaches 0 degrees. The line segment AB represents a liquid that is being cooled. At point B, we're now 100% in the liquid phase. We'll notice it flatlines as it begins to solidify. Point B to point C is a phase change known as the heat of fusion, taking the liquid and turning it into a solid. There will be one more line segment from point C to point D where we take the ice that formed and cool it even further from 0 down to negative 70. This particular problem will have 3 line segments involved. Line segment AB represents a liquid phase where we're cooling. Line segment BC represents the heat of fusion where we take the liquid and cause it to turn to solid. From line segment CD, we are cooling even further the solid ice from 0 down to negative 70. Again, where we have slopes of the line, we know it's MC delta T. Where we have a phase change, we use the constants provided in our problem. Also, going back and rereading, I need to know the amount of water we're working our problem for. I notice it gives me 75 grams of water. I also want to know the equivalent amount, but in a mole unit. I need to know both numbers to correctly match the units for each line segment. So I like to have both numbers ready. Sometimes we need mass for the MC delta T problems. 75 is our value here. But sometimes we need to know mole numbers when we're changing phase. 75 divided by the molar mass of water, which is 18, gives us 4.17 moles. So we have a mass measurement and an equivalent mole value, so we're ready to place in the correct number for each line segment. When we take a first look at that line segment AB, from point A to point B, we are changing temperature. We have a slope to the line. We know it's an MC delta T, where M stands for mass, C is the specific heat constant, and the temperature change is delta T. The mass we were given is 75 grams. The specific heat constant in the liquid phase for water, 4.184 joules per gram degree Celsius. And the change in temperature as we move from point A to point B, starting at 20 and going down to 0, it changed by 20 degrees Celsius. Let's also divide by 1,000 so we can report our answer in kilojoules of heat, knowing that we'll have to add like units at the end. The mass of 75 times our specific heat of 4.184, that's the liquid phase constant, times the delta T, the change in temperature of 20, and I'll divide that answer by 1,000, changing our joules to a kilojoule. I see an answer here on my calculator, 6.276 kJs. Our next line segment has us traveling from point B to point C, causing the liquid to turn to a solid. Freezing is that definition. we use the heat of fusion constant, 6.01 kilojoules in every 1 mole. The heat of fusion constant tells us how much energy it needs to cause the liquid to solidify. This is in a kJ per mole. To cancel the correct unit, we need to put the mole value in we calculated a moment ago, 4.17 moles, and just set that over a 1. When we hit, we'll already be in a kilojoule of energy. 6.01 kJs per mole times 4.17 moles gives us 25.06 kilojoules of energy for line segment BC. We have one more line segment to consider. We have a slope of the line from point C to point D. If we're changing temperature, we know it's an MC delta T problem. M in an MC delta T stands for mass. We'll need to plunk in our 75 grams that we began the problem with. We're in the ice phase. We need the specific heat of ice for this problem, which is given as 2.09 joules per gram Celsius. And to move from point C to point D, that's 0 to negative 70 degrees. That's a change of 70 degrees Celsius. Let's also divide by 1,000 so we can turn our joules into kilojoules of energy. There are 1,000 joules for every 1 kilojoule. 75, the mass of our water, times 2.09, our specific heat of solid water, times 70, the delta T, and I'll divide that answer by 1,000, converting joules into kilojoules. I'm seeing 10.97. 10.97 is our answer. The last thing we'll need to do is to sum the 3 line segments. 6.276 plus 25.06 plus 10.97. This value is 42.306, I'll round 42.31 kilojoules. Go back and consider, is this endo or exothermic? Starting at 20 and cooling it down shows us an exothermic process. Each one of our values was heat releasing exothermic. I'll let you know, I know it's exothermic by putting the negative sign, just as we did in the first problem of this objective. Remember, if I ended up drawing a graph that started low and went high, this process climbing high is endothermic, positive value. These problems just coincidentally both represented exothermic graphs. Both of these reported negative values. You've just earned an A+ on Objective 4.